video, we'll take a look at section 2.3 in your textbook, and it talks about finding limits algebraically. So in section 2.2, there was some discussion about finding limits from a graph, and today we want to move that into using some algebra, using some equations to find some limits. So I'll start off by just giving you a couple of examples of looking at a graph, and we'll see if we can come up with a rule that helps us to find those limits algebraically. So here's my first example. And in this example, we are looking to find the limit as x approaches 4. Remember, that is from both the right and left, because those limits have to agree in order for the limit to exist. And we're going to be looking at this linear function 1/2 x minus 7. So we want to find the limit as x approaches 4. And so what I've done is I've graphed that function just for a quick and easy sketch here of what that graph would look like. I use my graphing calculator. So I'm going to trace, and hopefully you can see, as I'm approaching x equals 4, tracing along the graph of this linear function. Right here I'm at 4.04, but that's pretty close. And so we can see as we approach 4 from the left and from the right, we are approaching the same value on this linear graph. And even though it looks like there's a hole at the moment, that's the cursor, there is no hole. Again, it's just a linear graph, so it is continuous. So it looks like we're actually approaching the y value of -5 as we approach x equals 4 from both sides. And so that is actually our limit here. Our limit is -5. So let's see if we can find another way of algebraically finding that same limit without needing to look at the graph. And so what we can do here is we can directly substitute our value into our function. And again, that method, direct substitution. If we take 1/2 and directly substitute the value of 4 into the function, you can see that we are getting that same value of -5. And if we take a look at the graph once again, because our function is graphed continuously, there's no holes or breaks, it's a pretty predictable function. As x approaches 4, y approaches -5 on the line graph itself, and again, there's no jumps, there's no holes, so our y value, our limit, is what, our y value is what gives us our limit there of -5. So let's look at another example. And in this example, I'm going to switch it up a little bit, and I'm going to use a nonlinear function, specifically a quadratic function. So if we take a look at the graph of this function, we have x squared minus 5, a parabola, and we want to look at the limit as x approaches -1. So once again, let's trace. And there I am, already close to -1. My trace function on my calculator gets me close to -1, not precisely at -1. So if we look as we're approaching it from the left-hand side and from the right-hand side, we are approaching the same value. There are no holes, there are no jumps, no discontinuities in this graph. So the y value itself, when we plug -1 into the function, is what gives us the limit as we approach -1. So once again, I can use direct substitution in order to find the limit. So I can take -1 and directly substitute it into the equation x squared minus 5. And it looks like I'm getting a limit of -4 as x approaches -1. Let's confirm with the graph. So it looks like here as I approach -1, my y value is -3.86, and if I were to get exactly at -1, I would have a y value of -4. So that's consistent with what we found algebraically. All right, so let's generalize this a little bit. Okay, so direct substitution for finding limits algebraically. That means we really don't have to look at the graph. We're going to do it algebraically. Again, using that direct substitution method. And it's going to be effective for any polynomial function. So polynomial, remember, those are going to be your linear functions, quadratics, cubics, any of those smooth continuous curves that have no holes or breaks or discontinuities. So any polynomial, we can use this method of direct substitution to find a limit, where we take the x value, plug it directly into the equation, and that tells us our limit, and we don't have to graph. Okay, so one of the other things that we want to look at here is an example of where direct substitution might cause some problems. Alright, so let's look at here direct substitution failure. Direct substitution failure. And more important than the failure, we're actually going to look at how do we correct it. How can we make it better? So here's an example of where we would have direct substitution failure. So let's say we were trying to find the limit as x approaches 2 of the function x squared minus 6x plus 8 over x squared minus 4. Okay, so here we have what's called a rational function. And let's try to plug 2 into the rational function and see if direct substitution is going to be a possibility for this particular limit. So if we were to plug 2 in, let's keep going and calculate what these values are. And I'll let you continue on that while I calculate as well. Uh-oh. It looks like we get 0 over 0. Uh-oh. This causes a problem, and I want you to take a second to think about what is the problem when we use direct substitution and we get an answer of 0 over 0. And hopefully your response to yourself is that your denominator, specifically the denominator, cannot equal 0 or should not equal 0. And so it's okay for the numerator to be 0. Sometimes we get limits of 0. That's okay. What we don't want is a denominator of 0. This is undefined, and so we don't have a limit here. But there actually is a limit when you look at the graph of this particular function. So we want to find a way to get around this and actually figure out the correct limit to this rational function. Now there's a couple of ways that we can go about that, and there is a technique called L'Hopital's rule. Some of you may be familiar with that rule already from perhaps taking calculus previously. L'Hopital's rule, and I'll just write that down here, looks like this when you spell it. I believe that's going to come up in section 4.7. So there will come a time, once we've proven a few more things in this course, where we can use L'Hopital's rule and find this limit algebraically. But we're not going to head towards that rule yet. We're not quite ready for that. So instead, what we're going to do is we're going to take this rational function and see if we can factor it and then hopefully cancel a factor. So this is the technique we're going to use whenever we end up with a denominator equaling 0. We're going to try to factor it and reduce it. So if we refer back to this original rational function, we can factor the numerator and factor the denominator. Two different factoring techniques. Hopefully those are pretty fresh in your mind. We're sort of reversing the FOIL process, if that's a term that you're familiar with from algebra, in the numerator here. And we're going to get x minus 4 and x minus 2. In the denominator we have a difference of 2 squares, so we get x plus 2 and x minus 2. And you can see that this x minus 2 factor does cancel for us. So that results in a new rational function, x minus 4 over x plus 2. So let's try to see if we can find the limit using our reduced form of our rational function, and perhaps we can use direct substitution successfully this time. If we use that direct substitution, we're going to get negative 2 over 4, which is going to give us negative 1/2, which clears up our problem. So that is, in fact, our limit as x approaches 2 for this function. That is the correct limit, and all we needed to do was factor and reduce this so that we don't have a denominator equaling 0. Now, we will, in this course, talk about what's happening here where these factors cancel and it's creating a whole. We'll also talk about the fact that we have some asymptotes going on here where our denominator equals 0. That gives us some vertical asymptotes. So that is something to consider. And I just want to refer you to the graph of this function. I'm going to zoom in a little bit so you can see this a little bit better. So I typed in the original function. You can see my equation at the top. This was before we factored and reduced. And here x is approaching 2. We don't have any holes at that point, so we're safe. We're going to have the same limit from the left as we do from the right. And you can see that we're getting almost negative 1/2, which is what it precisely is when x approaches precisely 2. So our graph does match what we got here when we worked through this algebraically, and you can see that the 0 over 0 that we initially got doesn't really match the correct limit. So that is what you need to know about section 2.3. There are times when you can use direct substitution, and that would be with polynomials. Anytime you're dealing with a rational function, you want to make sure that your denominator doesn't equal 0. And if it does, you want to try to factor and reduce and then use your direct substitution.